Hi class, welcome to Math 180. My name is Matthew Sokol and I'll be your instructor for the course. And what I want to do in this quick video here is I kind of want to talk about a little bit introduction to what we're going to talk about in Math 180, how it's different from Calculus 1, and then also talk about the two classical problems of calculus and where the study of calculus comes from. Okay, so what is this course? This course is much like Calculus 1, but with a focus on business applications. Okay, so some of the other big differences between this course, we don't do any trigonometry. All right, so Calc 1, when you take Calc 1, like a traditional Calc 1 course, you'll learn all the same basic concepts we learn in this course, but then you'll also expand on them to the trigonometric functions. We don't do any trig in this course. And Calc 1 courses focus on physics problems. And we won't be doing that in this class. Here it's a business focus. So hopefully you're in this course because you eventually want to be a business major, management major, or even an economics major. A little bit of side note, a little bit of history about myself. So I have 2 graduate degrees, one in mathematics and one in economics. And economics uses a ton of mathematics, a ton of calculus. So this course is fantastic to help lay a foundation if that's kind of the areas you want to go into. So don't feel like you're not going to learn calculus, because you will. It's just our focus will not be on any trigonometry, and our focus will be on business applications instead of physics applications. Okay, so where does the study of calculus come from? Okay. So where do the roots of calc come from? So when you think about your history of calculus, you think about Isaac Newton and discovering gravity and then his work there for calculus. But really, the study of calculus really got its case from 2 classical problems. Okay. The first is what we call the tangent line problem. And then the second is what we call the area under the curve problem. Okay, and what I want to do is I just want to kind of talk to you about these 2 classical problems, how they're eventually solved and how they relate to calculus, and then what we eventually are going to call the limit process. Okay, so the tangent line problem. So suppose you have this graph. Let's consider the function f of x is equal to x squared plus 2. Okay, you were to just roughly see what this graph looks like. Okay, this is just a rough sketch. Okay, looks something like this, right? Question would be something like this: what's the slope of the line tangent to the graph at, let's say, x is equal to 1. Okay, so at the point 1 comma 3. Okay, so here's the point 1 comma 3. So what we want to do is we want to find the slope of that tangent line. So tangent line just touches the graph. Okay. So to find the equation of a line, what you need is you really need the slope of the line. Okay, so you need to know 2 points on the line. So if you look at this problem here, I only know 1 point on the line, right? So, how would I even begin to find another point on the line? So traditionally what we do is, okay, we estimate this with the secant line. And what a secant line is it's a line that cuts through a graph at 2 points. So let me pick this line here. Okay, so we'll just call this line 1, L1. Does this line do a good job estimating our tangent line? No. Well, I picked a point that was way too far out here. Okay, let me pick this point here. So now let me draw line 2. So line 2 goes through here. So it gets better. It gets better, right? So, you know, what you're going to keep doing is you're going to keep picking lines that are closer and closer and closer and closer, okay? And so remember our slope, m, is equal to the change in y over the change in x, okay? But what you're going to do is you're going to pick points that get closer and closer and closer and closer and closer. So as you pick points that are closer and closer to the point 1, 3, what you notice is that delta x, the change in x, goes to 0. It gets closer. Okay, it gets closer and closer to 0 because you're going to pick a point here, and then you're going to pick a point here, 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 getting closer and closer and closer. So how do you, you can't divide by 0. So how do you find the value of a point that gets like infinitely close to 0 like this, okay? This is going to be called the limit process. And that's going to be the first topic we're going to learn about. Like how do you evaluate something, okay? Or as it goes towards a value. Not exactly as what it's equal to when delta x goes to 0, because remember you can't divide by 0. But what is the value as delta x goes to 0, gets closer and closer and closer to 0? What happens to the value of our slope? The second common problem is area under the curve problem, okay? So suppose you have this graph. And forgive me, my graphs are a little messy here. Okay, you have a graph that just looks like this, okay? And you want to find the area under the curve between 2 points, A and B. So you want to find this area here under the curve above the x-axis between these 2 points, A and B. So find area under curve above x-axis between A and B. So like there's no formula for this, right? There's no formula for this shape in here. So what you do is you can estimate the area with rectangles. Okay, so what I mean here is you're going to draw a rectangle like this. You're going to draw another one like this, another one like this, another one like this, another one like this, and finally another one like this. Okay? And then you're going to find the area of each rectangle, so sum the area of the rectangles. And that's going to be how you're going to estimate the area. But now here's the thing. You'll obviously know, right? Like area is equal to the length times the width of each rectangle. Right? So our width is going to be the delta x. So the width is going to be the distance from here to here. Well, obviously I could do better than these rectangles, right? These rectangles obviously underestimate the area. So how would you do better? A better estimate, more rectangles. And you're going to keep decreasing delta x. And you're going to look as the width delta x goes to 0. Okay, because you're going to have more and more rectangles. But like obviously then if delta x goes to 0, the area of the rectangle is 0. Okay, so how are you going to evaluate this process? And so we're going to learn a method later on. It's going to be called integration for this, how to solve this problem. Okay, and these are the two problems that we're driving towards in this class. And I'm incredibly excited for our time together and the semester together. And so our course is going to start by learning about this limit process. okay? And then we'll learn about something called the derivative, or how to take a derivative. And then we'll end our class talking about it. Again, we'll look back at this area under the curve problem and talking about integration.